Welcome to Fluid Mechanics N6. Today's presentation is going to be on Pelton wheels. Let's begin. First, let us look at the working principle of a Pelton wheel. You will remember when we did the video on water turbines, we saw that you have two types of water turbines. The first type is the reaction turbine, and the second type is the impulse turbine. And so the Pelton wheel is a classical example of an impulse turbine. Pelton wheels are particularly useful when you're dealing with conditions where you have high heads and low flow rates. I repeat, conditions where you have high heads and low flow rates are perfect for a Pelton wheel. And so you will need to remember that for Pelton wheels, generally the situation that you will be dealing with is one of high heads and low flow rates. And so what you see on the screen here is a full assembly of a Pelton wheel. The Pelton wheel is actually here, sometimes referred to also as a runner. And you will see that you have buckets that are mounted all around the Pelton wheel. What you see here are buckets. And so these buckets are mounted on the Pelton wheel, and as the Pelton wheel is rotating, the buckets, of course, because they are connected to the wheel, will be rotating along with the wheel. What you see here is the nozzle through which the jet of water is released, and inside of the nozzle you have a spear. Okay, this thing here, this is what we call the spear, and the spear is used to regulate the flow rate. You can imagine if you push this spear to the right, of course it will close the opening of the nozzle. The more the spear is pushed to the right, the more the spear head will close the opening of the nozzle, and so it will reduce the flow rate. And the more you push the spear to the left, okay, the more the spearhead will will pretty much move away from the opening of the nozzle, and in that way open the flow. And so this spear is then used to control the flow rate of the nozzle. It is important to be able to control that flow rate because that allows us to control the amount of power that is produced. Okay, so sometimes there is a need to control the flow rate that is released through the nozzle, and so that is done by means of the spear that you see. And so you can see that the jet of water from the nozzle is from left to right. Okay, so this water is ejected from left to right. Okay, and then when it goes that way, it comes and makes an impact with the buckets. And because the impact is from left to right, this causes the buckets and the wheel to rotate in the anti-clockwise direction. I hope this is easy to see. And so this wheel, together with the buckets that are mounted on it, will be rotating in the anti-clockwise direction because of this jet of water that is coming from left to right. Okay, and so that is quite important to be able to see. And then another thing I will point out is that the buckets, as they rotate, of course they will describe a circle. Okay, and you can see here in dotted lines you have a circle there. Okay, that is described by the buckets as they are rotating. And so that circle is what is called the pitch circle, but also sometimes it is called the bucket circle. So if you come across the expression pitch circle or bucket circle, this is just the circle that is described by the buckets as they rotate with the wheel. Okay, and you can see it in the figure here in dotted lines, and it is passing by the center of gravity of each bucket. Okay, so this circle, that is what we refer to as the pitch circle. Very, very important. And so when you look at the bucket in 3D, this is more or less what it looks like. What I want you to be able to see is that you have a shape here that will split the jet of water. So as the jet comes in this direction, because of the split that you see here, the jet will then be divided, and some of it will go that way and the other portion will come in this direction. So if you look at the somewhat top view of the bucket, which is what you see here, and you have the jet of water that is coming, which we refer to as the incident jet. And so this jet is coming with a velocity vi, and then it comes and it interacts with the bucket. And as you can see, you have this split here to split pretty much the jet of water. Some of it will go in that direction, and the other portion of the jet of the water will come this way, okay? And so if you see in this particular figure, the jet of water is deflected at an angle of 180 degrees because it was coming horizontally this way, and then it returns in the opposite direction but still perfectly horizontally. So if you try to measure the angle between this and that, is pretty much 180 degrees. Okay, so this will be a perfect deflection of the water, because when you manage to achieve a deflection of 180 degrees, that means that you have created the maximum impulse force that you can create. This is only true theoretically, okay? We can only think of it theoretically. In practical applications, it is not quite possible to design a bucket that will be able to deflect the water at 180 degrees, okay? You cannot have a perfect deflection like that. It doesn't matter how good your bucket design is. Generally, what you will manage to achieve is a deflection angle of about 160 degrees. And so what you see in the figure here is only something that we can look at theoretically, okay? But in practical applications, a bucket will not be able to deflect the water as you see in the screen here at an angle of 180 degrees. And so the incident jet comes in with a velocity vi, and of course the bucket is moving with its own velocity, which we will refer to as u. Okay, what I wanted you to see is that when you look at a bucket in 3D, in the middle of it you have a shape that allows the jet of water to be split and to be sent in two different ways. Okay, and you can see here the split occurs at this point here, and the jet will go in this direction and then in that direction, and because of the shape of the bucket it gets deflected backwards. Okay, however, the deflection angle, it cannot be 180 degrees. It's usually somewhere around 160 degrees. That is in practical applications. Theoretically, we can look at cases where the deflection is 180 degrees, but in practical applications you cannot design a bucket that is that perfect. Okay, having said that, let us look at some of the things that affect the efficiency of a Pelton wheel. The first one I am going to speak about is the number of buckets. Remember, the efficiency of the Pelton wheel is dependent on the impact of the jet of water on the bucket. And so if you do not have enough buckets on your Pelton wheel, okay, if you do not have enough buckets on your Pelton wheel, then some of the jet of water will make no impact with buckets, will just come out. It will just come out of the nozzle and fall down, okay? So you need to have a sufficient number of buckets so that the jet of water will always be making impact with the buckets, okay? If the number of buckets is not enough, then some of the water will just make no impact, and so in that way power will be lost, and so you will affect the efficiency of your Pelton wheel. The second thing that affects the efficiency of the Pelton wheel is the shape of the bucket. As I said to you, for you to maximize the impulse force on the bucket, you want the jet to be deflected back at an angle of 180 degrees. But this is not achievable practically, and most of the buckets can deflect the water up to about 160 degrees. But if you have a bucket that is poorly designed, then of course it will maybe deflect the water at 120 degrees. And if that's the case, the impulse force on the bucket will be even lower, and that will mean that the power that is generated by the Pelton wheel is also low, and in that way its efficiency will be affected. Okay, so the shape of the bucket is very important. You want to design a bucket that is capable to deflect the water back at an angle as close to 180 degrees as possible. Next, the size of the bucket also affects the efficiency of the Pelton wheel. If you design a bucket that is too big, what will happen is that you will reduce the number of buckets that you can have on the wheel, because if each bucket is very big, then you cannot have as many buckets maybe as you should have on the wheel. And for that reason, then again, some of the jet of water will not be making full impact on the buckets, and therefore you will not generate as much power as you should, and that will affect, of course, the efficiency of the Pelton wheel. And you also have friction that is always a hindrance to our power producing capabilities in mechanical engineering. Whenever you're dealing with a mechanical device, you will always have friction as an issue. And with a Pelton wheel, friction will occur between the water and the air. Okay, as the water is coming out of the nozzle, it will of course interact with the air, and you do have some friction there, and that will of course affect the velocity of the water, and hence the impulse force, and also therefore the power that is generated by the wheel. But the second type of friction that you will have in a Pelton wheel is that between the water and the surface of the bucket. Okay, and that will also affect the power that you will be able to produce with that Pelton wheel. The last thing I am going to speak about that affects the efficiency of a Pelton wheel is the wheel speed. Imagine if this wheel was rotating very fast. What will then happen is that some of the buckets will not be properly impacted by the jet of water, because as the water is coming to make contact with the bucket, but because the bucket is going around very fast, because the wheel is spinning very fast, then of course that bucket will move away from the jet before the jet has had a chance to actually make a real impact on it. And so the speed of the wheel can also affect the efficiency of the Pelton wheel. Okay, so these are very important to note. What I want you to be able to see here is that the bucket is key if you want to achieve a good efficiency of your Pelton wheel. You need to be very careful in the design, the placing, the shape, and the number of the buckets. Okay, very, very important. The bucket is key in the performance of your Pelton wheel. Okay, as you can see, the efficiency is quite dependent on the bucket, the number of buckets, the shape of the bucket, the size of the bucket. Okay, so this is very important. Now, let us look at the velocity diagram of a Pelton wheel. And here we will just look at the jet of water and its behavior with a bucket. So as you can see here, we have incoming water, and then it interacts with the bucket, and then it goes out this way. And so what you have here are incoming or incident, or if you want, you could also say inlet conditions of the water, okay, in terms of velocities. And here it's the outlet triangle, okay. So the water comes in this direction and interacts with the bucket and then comes out this way. And so we can look at the incident jet of water and look at all the velocities that we have here. And so at the inlet, you have U that you see